Welcome. We will do one more example of graphing using calculus of an explicitly given function. This time we are going to do the problem from scratch. To keep the calculation short, we will again do a simple polynomial. 3x power 4 minus 4x power 3. So we have to find the first and second derivatives, the critical values, the points of inflection, sign charts of y prime and y double prime, and put all of this together. The differentiation part is easy because all I have to do is apply the power rule term by term. The first derivative is 3 times 4x cubed minus 4 times 3x squared, which simplifies to 12x cubed minus 12x squared. Since I have a polynomial, it's always differentiable. So the only critical values occur where y prime is 0. To do that, I have to factor y prime. So we can factor out 12x squared. I get 12x squared times x minus 1. X squared is 0 when x is 0, and x minus 1 is 0 when x is 1. So those are the critical values. To find the critical points, I need to plug this back in the original function and find the y coordinates. Let's also find the points of inflection. So the second derivative is the derivative of the first derivative, so that's 12 times 3x squared minus 12 times 2x. Or 36x squared minus 24x. Again, we can factor this by pulling out a 12x. And the other factor is 3x minus 2. So 12x is 0 when x is 0. 3x minus 2 is 0 when x is 2/3. So those are the x coordinates of potential points of inflection. Let's also find the x-intercepts. X-intercepts occur when y is 0. Again, because I can factor y, we can find the x-intercepts easily. I can factor x cubed out of the two terms in y. So y factors as x cubed times 3x minus 4. And this is 0 when x is 0 or when 3x minus 4 is 0. 3x minus 4 is 0 when x is 4/3. So 0, 0 is a critical point, a point of inflection, and also an x-intercept. The other critical point occurs when x is 1. If x is 1, y will be 3 minus 4 or negative 1. So those are the two critical points, 0, 0 and 1, negative 1. It's an inflection point at 0, so that's 0, 0. The other inflection point occurs when x is 2/3. So you plug in 2/3 for x and simplify the value of y. I will leave the arithmetic to you. It comes out to be negative 16 over 27. It's about 0.6. And we already found the x-intercepts, 0, 0 and 4/3 0. We can proceed as we did before, do the sign chart separately first. But if you're doing a problem from scratch, sometimes it's easier, even if it takes a little bit more work, to first find the intervals and then do the signs in each interval. Just mark the x coordinates of the critical points and the points of inflection. They would be at 0, 2/3 and 1. So the intervals I get are negative infinity to 0, and then 0 to 2/3, where I have a point of inflection, 2/3 to 1, where I have a critical point, and then 1 to infinity. 4/3 is an x-intercept that doesn't really matter for the sign charts. I'm going to do the sign chart by doing test values. So I take some x coordinate in each of these, plug that into y prime and y double prime. We can use the factored form. At negative 1, x squared is positive, x minus 1 is negative. So y prime is negative. And for y double prime, I have 12x times 3x minus 2. They are both negative when x is less than 0. So y double prime is positive in that interval. So I have a function that's decreasing and concave up. So we draw an appropriate segment. Between 0 and 2/3, I can take 1/2 or 0.5. Again, 12x squared is positive there, and x minus 1 is negative, so y prime is negative. In y double prime, 12x is positive, 3x minus 2 is negative, so y double prime is negative. So the function is decreasing and concave down. From 2/3 to 1, again 12x squared is positive, x minus 1 is negative. So y prime is negative. In y double prime, 12x and 3x minus 2 are both positive, which means the function is decreasing and concave up. In the last segment, 12x squared and x minus 1 are positive, so y prime is positive. 12x and 3x minus 2 are both positive, so y double prime is positive. So the function is increasing and concave up. And this gives us a rough graph of the function.